we discussed diffraction from a single slit. So what happens when light passes, when a parallel beam of light passes through a diffraction slit? One slit. So if you have one slit, what happens is, so for one slit, you have the diffraction envelope creating light on the screen. So basically this is a screen. This is just showing you the intensity of how much light is available here and how much is here and how much is here. We call this the diffraction minima. This is a diffraction minima, that's a diffraction minima, and that's a diffraction maxima. At what angle will this appear? This appears at an angle d sine theta is equal to lambda. What is capital D standing for? The width of the slit, the gap. So this is d sine theta equal to lambda, and this is d sine theta equal to 0, and that's also d sine theta equal to lambda. So that's a condition for the first minimum. And it can go on. This is what happens when you have one slit. When you have two slits, what happens is you have the diffraction envelope the same way. So the light is available exactly the same way, but you will see interference peaks coming inside. Because there are two slits, you will see interference peak. So that is an interference peak, the next one, and goes on. So this is what you'll see on the screen. So will you see brightness in this area? No, because this part corresponds to interference, destructive interference. This also corresponds to interference which is destructive. Because of that, even though diffraction allows light, that light is going to be destructively interfering because of the two slits. So these things, what you see here, the blue peaks, those are the interference peaks. And for interference, this position corresponds to the minimum of interference. And the condition for this, for interference, it depends on how much is the slit separation. Okay, I did interference in detail. What is interference? When you have two sources next to each other. So when there's a source S1, when there's a source S2, the light coming from these two sources will interfere on the screen in such a way that will form bright, dark, bright, dark, bright. And that's a central brightness, which is this. And this darkness that you see here is this one. And then the next bright is the next bright here. So where will this first brightness come in? Now this distance from one bright to the next bright is called X, which is, what is X? What is that?
Bandwidth.
Bandwidth. So that's a bandwidth. And this X, the distance from one bright band to the next bright band, I derived it as lambda L over D. So you can expect more of this separation depending upon what wavelength you're using. So if it is for red, you'll get more separation. For violet, it's going to be less separation. Distance on the screen. So if the screen is further away, then of course you're going to get more bandwidth. That is separation between brights and darks, or brights. And then the next factor is D, which is the distance between the slits itself. That is D. So if the distance between the slits is D, and if it's a small distance, you can expect more bandwidth. Okay, so this is the idea of interference. So why we are seeing bright, dark, bright, dark, bright, dark in that orderly fashion is because we're using two slits. So wherever diffraction is allowing light to come through onto the screen, interference will also happen. And this one will happen at what condition? What is the condition for that? D sine theta is equal to 0. And this one happens when d sine theta is equal to lambda and that will be 2 lambda and so on. And in between here the condition is d sine theta is equal to half a lambda. That will be for lemma. So this is what you'll see on the screen. Bright and dark patterns. And I showed it to you here using a laser. Okay? What happens as we increase the number of slits? When we make it 3 slits, what happens is you have the interference peaks exactly in the same place, but you'll find an extra and so on. You will see an extra peak coming in between, and they are called the secondary interference. These are the primary interference peaks, and these are called the secondaries interference peaks. Yeah.
What are like the first degree and second degree interference? What's that concept?
What is first degree?
I don't know, it was on the homework. I didn't understand.
First order?
Order, that's what I meant, yeah.
Yeah. First order, second order.
So it's the primary one, but it's just which one out?
Yeah, this is the first, and that's the second, and that's the third. Goes like that. Remember I showed you towards the end dots at different places? That's the 0th order. This is 0th order. And that's the first order. And the first order. Second order. Second order. Yeah, we'll get there.
Okay.
And these are called the secondaries. Now what happens when the slits numbers are increased? If you use 10 slits, then on the screen what you see is these peaks become narrower. They are still there at the same location, but they become narrow. And the secondaries become more in number. And how many of them? For 3 slits, you have 1 secondary. For 10 slits, you will have 8 of them. And these are the 8. So, observations, the interference peaks become narrow. Secondaries grow more in number, which is 2 less than the number of slits. And the secondaries become low in intensity. And that's what you see. So if you use 100 slits, then it's getting that way. Now what happens when you use too many slits, which is like 1,000 slits? When you use 1,000 slits, why is the diffraction envelope exactly looking alike? Even though you're increasing the number of slits, the slit width, the capital D, still stays the same. It's just that you're increasing the number of them, that's it. So you're increasing the number of them, but the capital D is still the same. Now, when you use 1,000 slits, you'll see just one line right there. There's next line, there's the next line. Now these are just the interference peaks, and they come in a region where diffraction allows light to come through. And because the diffraction's intensity is coming down, that's why these peaks get fainter and fainter. Yeah.
Why are the not so bright points not shown on there? Like the lower intensity? Like where are those not?
Because they fall into the diffraction minima area. And you're talking about the next one?
I'm wondering why isn't there just like a horizontal line?
The secondary.
Oh, the secondary is because there are so many of them and they kind of go down in intensity so much that you don't see them at all.
I'm wondering like why are the other ones not touching the x-axis, but
Oh, this is not an axis.
well, I mean just the line. Like why are they not?
I mean,
What number of steps do you have?
it is. This is just showing the relative intensity. It's not. It's not anything. I mean, like this. This whole intensity is going to come off. See, actually, you can see some intensity here, some brightness, but that kind of completely collapses because the number is so many and the intensity is so weak. That's why I kind of touched it there. So there is nothing here. No brightness. Just that brightness there, and that's what you saw on the screen when I showed it. Okay. Now, when you have 1,000 slits like that, that is what we actually call as a diffraction grating. Diffraction grating. By the way, there's one more correction I have to do, which is, what is the condition for this one, the peak? What is the condition I wrote down? D sine theta is equal to? What is a D? Slit?
Separation.
Okay, now I'm going to zoom it up a little bit. Here is the first slit. That's the first slit. That's the second slit. That's the third slit. Now what is the distance from here to here? What is it? Capital D. And what is it? Where is small d?
The separation between two slits.
From here to here?
Isn't it to the screen?
It's from the middle of the slit
To the mid, from the middle of the slit to the middle of the slit.
to the middle.
Which basically means from here to here, right? So actually what we are talking about, that small d, is actually the sum of this and this separation. It is both. This and this together, that is what small d is, not actually just the distance, not say this is one slit and this is the other slit, it's not just this. It is from center to center. You get it? Or from edge to edge. From this edge to this edge. That will be the actual D we are talking about. So the D is actually here. You get it? The D that we are writing there is from here to here. So, and what is the expression for this? What is the condition for this one to appear? The condition for that one is d sine theta is equal to lambda. What is the condition for this one? D sine theta equal to 2 lambda. Right? And so for each of these lines, you have a condition. And the condition is d sine theta is equal to m lambda. Now what is m standing for? M stands for the
Order.
order. We call it order of diffraction. Although it is interference, we still call it order of diffraction. So we call it order. And the order starts from 0. M is 0, 1, 2, 3, etc. Okay? So this is of order 0. This one is a first order diffraction. This is called the second order diffraction. And you may have a third order diffraction, possibly. Okay? Sometimes it's so feeble that you don't even see it. But the most stress is given to the first order because that will be more bright. The first order. Okay? So this gadget, which actually has multiple slits in them, that is called a diffraction grating. Now what's that equation again? D sine theta is equal to m lambda. D is the distance from here to here. If the distance from here to here is d, how many slits are there in 1 meter? There you go. 1 over d, because d is the distance from here to here. How many such distances are accommodated in 1 meter? It will be 1 over d. So sine theta. Okay, there you go. So sine theta is equal to m lambda over d. Is that right? From here to here? And 1 over d stands for number of slits per meter. So sine theta is equal to n m lambda. This is called the diffraction formula. That's called the diffraction formula. That is called the diffraction formula. Capital N stands for number of slits per meter. M stands for the order. M just stands for the order. Which order are you talking about? And lambda is the wavelength that is used because we have to use a monochromatic source. Theta is the angle at which it appears, right? Theta is the angle of diffraction. And N stands for the number of slits per meter. M stands for the order. We talk about this one as a zeroth order. That is zeroth order. That's a first order, second order. And on the screen you saw the zeroth order is the brightest one. And then the first order on both sides were not as bright. Okay? You get it? So that's the diffraction formula, where N stands for the number of slits per meter. Of course, the unit is per meter. And so when I say there are 1,000 slits per centimeter, in 1 centimeter, if there are 1,000 slits, what will be capital N? If there are 1,000 slits per centimeter, sometimes they give you per centimeter. What is N then? If N is 1,000 slits per centimeter, what will you put N as? Huh? 100,000. If in 1 centimeter you have 1,000 slits, you have in 1 meter, of course, it's supposed to be more. Okay? So if you have 1,000 slits per centimeter, sometimes they give you in centimeters. So you should not be using this number there straight away. You have to use it per meter. So just take care of that part. Very commonly, they can give you in centimeters. Or sometimes they'll tell you, okay, here's the diffraction grating of this size of 2.5 centimeters, and it has so many lines. So they give you the size, and they tell you how many lines are there. But you can't use that straight away. You have to get it in per meter and then substitute it there. Then only that formula works. So that's called the diffraction formula. All right, now that is called the diffraction formula. Now what will happen if you use white light, not monochromatic light, but just white light? Yeah.
Each individual wavelength will have its own diffraction
Yeah.
pattern.
What will be the color right there?
White.
That will be white. This will just be white. You know reason? The reason is, why is this one white? Because all the wavelengths for the zeroth order, all the wavelengths, whatever wavelength you use, the angle is expected to be 0, right? So the order 0 will imply simply angle is 0. That means all the wavelengths will hit here together, so that will be surely white. But the first order, which one is diffracted the most? Which color is diffracted the most?
Red.
Red is diffracted the most. Watch this. In the equation sine theta is equal to nm lambda. We are talking about the first order, so m is 1. And we are talking about one grating that you're going to use, which means n is also fixed. So sine theta is proportional directly to wavelength. Red has a larger wavelength, so the angle for red is going to be more. So what will be seen on the screen, you will see red diffracted most and violet diffracted less. You get it? What about on that side? Red diffracted most and violet diffracted less. And all the other colors are going to be in between. All the other colors are going to be inside here. So this is white and this is colored like this. What about this one? This also will have a red. Oops. Will have a red and a violet. So we call this the first order diffraction spectrum. So you're getting a spectrum of colors. And this is the first order diffraction spectrum also. That's the second order diffraction spectrum. And that's the second order. So you can get more number of orders of spectrums. Now where have you seen spectrum before?
Rainbow.
Using a
Prism.
prism. When you use a prism, you get one spectrum. When you use a prism, you get one spectrum. But that spectrum is not a pure spectrum. It's very difficult to get a pure spectrum. Why? Because to get a pure spectrum, you need a parallel beam of light. So to get a perfectly parallel beam of light is going to be hard. Okay? If you get a parallel beam of light, then only you can get a pure spectrum. Otherwise, what will happen, if you have a source here, then the light that's going like this, it will bend around, and this will produce its own spectrum, and this will produce its own spectrum, and the spectrums can overlap. The spectrums can overlap, so you will get not a pure spectrum. So the prism normally does not produce a pure spectrum, but a grating produces a very pure spectrum. It produces very beautiful spectrum if you are actually using a proper grating and a proper instrument to observe it. The instrument that we use to observe diffraction spectrum is called a spectrometer. It's called a spectrometer. So what we do is we have a diffraction grating installed. We put a small narrow beam of light through it, and once a narrow beam of light goes through it, it actually diffracts, and it will form the first order, second order, third order, and all that. And you can actually move the telescope of the. So how does the spectrometer look like? It's got a table. It's got a. This is called a collimator, and the collimator's main job is to collect light. It collects a light and sends it parallel. That is the job of the collimator. It has a bunch of lenses here. So what it does is it sends it parallel. It takes a light and sends it parallel. And of course there's a slit here to narrow down the light to a single slit. So light comes through a slit and goes through onto the table. Now what is kept on the table is a diffraction grating. It's kept like this. The diffraction grating is kept like that. Okay? Now what happens to the light when it comes out from there? The zeroth order will go straight out. Okay? The first order will go here. The second order will go here. And if you put a screen, you're supposed to see it on the screen just like that, right? But instead of seeing it on a screen, we use a telescope. To see it. And where is the telescope mounted? The telescope is mounted on a table. No, that's a different table. And this telescope can move like that. And as the telescope moves, you can actually figure out what angle it has moved. So there's a window here that tells you the angle. You understand what I'm saying? So if you keep the telescope straight, it'll read 0. And the slightest movement of the telescope, you'll see the reading is changing. And this is calibrated to read in fractions of a degree. Very tiny fractions of degrees, which means there's a vernier attached here. You know what a vernier is?
Vernier caliper?
Just like a vernier caliper. Just like a vernier caliper, but the whole thing is connected to a vernier, which means you will be able to read the angles very precisely. Not like 1 degree, 2 degrees, and 3 degrees. It will be like 0.01 degree, 0.02 degrees, like you can go up to there. Okay? So angles can be very finely measured using an actual spectrometer. So what is a spectrometer used for? Okay? What is a spectrometer used for?
Finding colors. Finding the absorbance.
You can find the wavelength of a light which you don't have an idea of. What do you have to do? Send the light through the spectrometer. Just send it. N is already known to you. You already know the N. So N is known, right? And if you're searching for the first order, then that M is also known, right? Can you measure the angle with the spectrometer? So when you you have some kind of a faint green color, I don't know where that, what wavelength it is, shine that light. Let it go down. When it goes down, it gets diffracted. You're not interested in the second one because it's like dim. You're interested in the first one because it's brighter. Get it? And then you look at the first order and find out where that green light is coming out. Once you locate the green light, focus it exactly on the crosswire to get the angle. Once you have the angle, substitute into this equation and get the wavelength. We can measure the wavelength of colors very precisely using a spectrometer. Do you get it? So if you want to measure the wavelength of any light, you can actually do it. And this is something that is used in atomic spectra, line spectra. You must have done something in chemistry. Have you done something in chemistry? Yeah. What is a line spectra? We're going to talk about this chapter later on. But what is this line spectra? In chemistry, how do you identify a material? To identify a material, there's something called flame test, right? So what you do is you take a sample of that and burn it. When you burn it, it emits a certain color. And you look at the color and say, all right, this is kind of brick red, so it should be barium. Oh, this is kind of greenish, so it should be copper. So you decide on which substance it is by just looking at the color only. But there can be different shades of green. Look at that green and look at that green. They're all different shades. You can get confused on whether it is this or that, So flame test just uses your vision, nothing else. But a spectrometer, it actually measures the actual wavelength of that light that's coming out. For copper, it should have one wavelength. And if it's coming from a different element, it should have a different wavelength. Every wavelength coming out from every different atom, they are all unique. No two wavelengths are alike. No two lines emitted by two different atoms are alike. So they're all unique. It's like fingerprints.
So can you trace it back to a light? So it's like fingerprint?
What is that again?
Never mind.
So you understand what I'm saying? Yeah.
So the spectrometers we used in APDM were used to calculate like the absorbance of a certain type of liquid or something. You put it in a test tube down there. Is that like a different type of spectrometer?
What did you do to observe it?
It's like we put whatever the substance was in a test tube. You put it in the spectrometer, and then
You put what in the spectrometer?
Liquids.
Oh, you just
we were looking at the absorbance of liquids.
okay.
Oh, that sounds like fun.
And then what are you looking through?
You're not looking to.
It just gives a calculation.
You set the length, the wavelength on it, and then it tells you the absorptivity. Or not, or the other way around.
Oh. There could be some other methods, but is it a very concrete one? Like, is it very precise?
It was really good.
Okay.
I'm saying those are just like different types of spectrum.
Yeah, there are different. There's something called absorption spectrum. Maybe probably it's using that technique. But what we are doing is kind of light. You burn the substance, and the light that comes after the burning passes through the spectrometer, and then you just measure the wavelength. Thereby, you know exactly what is coming out. So you can't make a mistake. So that's the basic idea of spectrum. So this is an impure spectrum, and this one produces a pure spectrum. It produces a pure spectrum. And why it's very pure is because there's no mix-up between the different spectrums that are produced. This is the first order. That's it. And that's the first order on this side. That's the zeroth order, which is supposed to be white. So if you pass white light through a grating, you should be able to see these. And a diffraction grating is what is used to measure the wavelength of a light that you don't have a clue about, right? Yes.
If you send instead of white light, say you send just a color of a certain wavelength, would you see at the different orders? Would you see the different shades of that color?
You will get the different wavelengths. Yeah, you will get different lines for the different stuff that is there. Sometimes, if you have a mixture of gases, for example, you have a mixture of gases. You have oxygen, hydrogen, nitrogen, all three, and then you burn it. When you burn it, it will emit a color. Send it down. And the spectrometer will split up those. The hydrogen, it has its own wavelength, it comes to a certain line. And oxygen goes somewhere, nitrogen goes somewhere. And then what you do is you look at those lines and measure the wavelengths of those lines. And then match it up. There's a table of elements and what wavelength it comes out. So you go through the table and find out, okay, here is the answer I got for the wavelength. Matches with what? Or matches hydrogen. That means the gas must be containing hydrogen. So you can actually detect unknown substances just by using a spectrometer. You got a substance and you want to study it. Spectrometer. Like imagine there's a sample from the moon. What is that? What material is this? You got a sample. Okay, burn it. Send the light through a spectrometer and calculate the wavelengths. Match up with your table of elements and you'll see that, oh, this is osmium. Okay, so is there osmium on the moon? You get it? So we look at the wavelengths and then decide what element it is. Yeah.
Is that how the Mars rover finds out what is in the soil? Is it just take a sample and burn it and then calculate it and send it out?
Yeah. It actually studies the spectrum. So basically the spectrometers are there, right there.
Yeah.
It actually kind of checks the wavelength immediately and then studies it. I mean, they're all automatic these days. A lot of these things are done not just manually. Yeah.
If you're a diamond guy, you gotta check if a diamond's real. Could you shine a light through the diamond? Or would you have to burn the diamond? Since people are selling you fake diamonds.
There is another method called absorption spectrum where you don't have to do any burning. You just let it pass through. When you let the light pass through, and if it is picking up its own wavelengths. Now diamond is just carbon. And because it's just carbon, it will just exhibit carbon's behavior. Now, if it is not diamond, and if it is like silica or something like that, then of course it will show the difference. Yes.
How exactly do we create white light?
How?
From the sources? Yeah.
White light is just a mixture of all the different energies put together.
I know, I'm just how do you get whatever, a light and then all those different wavelengths?
Continuous spectrum. That's called a continuous spectrum. If I have a light bulb, a heated filament, heat. When you just heat up something, the heat is going to spit out all the different kind of wavelengths. And if you actually look at that, that is called a continuous spectrum. Like if you study through a prism, you'll see smooth transition of colors. You saw that, right? Or when I use the prism. When I use the prism and white light, you could see the smooth transition from one color to the other color. That's called continuous spectrum. Whereas if it is coming from not a light bulb, but from burning of substances, then it will have discrete lines. So you won't see smooth lines everywhere.
So then how do we get like a laser? Just like one wavelength of light?
Laser, because you're burning, you're exciting one crystal, which is like ruby, or depends on what crystal you're talking about. Like for red, it is ruby. So we use that crystal, and exciting that creates the wavelength. And in a laser, it just is, laser basically, what is the full form of laser?
What is what?
Full form of laser. No, what is the full form of laser?
Laser on. Laser is
Like what is LASER standing for?
lights.
It's not one word. You know that, right?
Lights.
It's light amplification by stimulated emission of radiation. That's what it stands for.
There's radiation.
Yeah. Light amplification by stimulated emission of radiation. That is what LASER stands for. So it's not like one thing. Light so you're amplifying light by stimulated emission, like you repeatedly, like stimulate the emission, and then make that emission kind of bounce between mirrors, and then finally collectively let it go out.
By stimulation of emitted radiation.
Emission of radiation. What is radar standing for? What is radar standing for? Radar.
Oh, we don't analyze these things.
Again, those are not one word. It's radio detection and ranging.
Just radiation.
Radio detection and ranging. That's what it is. Yeah. Let me explain again. So there is a diffraction grating right there, and there is a little slit over here. And when you shine light through this, let me see if I can put this. If I shine white light through this, trying to get that.
I've seen some pretty good legally blind if you don't see anything, David.
Well, you can't see it on the screen. I'm trying to get it on the screen somehow, but no. Yeah, you look through the diffraction grating, through the grating, not through the little thing.
He's got like 50.
Yeah.
He's got 50. He's got another one. He's got
I can see indigo. Can we take it out?
Oh, you can't do Not real.
Oh! Missed it, okay. You're too far away. I have some more you want.
You trying to get a pencil in here? And what you did?
I've got some more if you want to take it.
So,
Oh, can you take a picture of that?
Yeah.
Oh, good. Shine it to the light, then it will be much brighter.
No, it's brighter away from the light.
Now, diffraction grating is understood. A spectrometer is the instrument that is used to observe the spectrums. Now, what we just saw was just one tube, but an actual spectrometer will have a collimator and a telescope, and the telescope is mounted on a turning table, which is calibrated to read angles very precisely. And so initially what we do is, when we're using the spectrometer, what we do is we put the grating, we look at the central one, bring the telescope right to the central one, and then set this to 0. We set it to 0 exactly. Once you set it to 0, then you can measure all the angles between here and here. Normally this is the angle that we look for. But if you measure this angle, and I can use this equation and put m equal to 1. But if I measure this angle, then you can put m equal to 2. and it should satisfy that also. So the wavelength will be exactly the same. So yeah, the diffraction grating is used for spectrometry. Yeah. And if you want to study the spacing of atoms in a crystal, they use spectral studies. How do they use a crystal? How can you diffract a crystal? A crystal is a set of atoms, right? Arranged. So there are a set of atoms. There's a gap between the set of atoms. So the gap between the set of atoms acts as a slit. And the atom itself is a separation. Do you get it? So if you have a crystal, the crystal will have a set of atoms here, another set of atoms, another set of atoms. So basically what's happening is you can see there are many slits. So a crystal acts as a diffraction grating. You get it? A crystal acts as a diffraction. Now, what is the space between atoms? It's much smaller, right? Of what order? So, if I take a crystal and pass light through that crystal, if I'm passing light through the crystal, remember the wavelength of light is compared to the crystal separation. This distance is very, very small. Now, if you look at the formula, d sine theta is equal to m lambda. The d is going to come down here. For a crystal, the d is very, very small compared to the wavelength is so big. So what will happen to the angle? Where will you see the first order? The maximum possible is 90. It can't go more than 90, right? So if lambda is too big compared to this d, you will not see any angle of diffraction because it's supposed to diffract more than 90 degrees. Do you see what I'm saying? So visible light cannot undergo diffraction through a crystal. So what is needed then? Because the wavelength of visible light is too big, that is why crystal is not doing anything to visible light. So if you send visible light through a crystal, is diffraction taking place? Yes. But the angle is too much that you don't even see anything. You get it? Because the crystals, the spacing is so fine that you won't see diffraction at all. Now what if the spacing is too big? Then also you won't see diffraction like the window. So what is needed for diffraction to be visible? The wavelength and this gap should be close. They should be close. So what kind of wavelength is used? X-rays. Because if you look at X-rays, the wavelength of X-rays and the spacing between the lattice spacing, they are matched. The wavelength of X-rays is like 1 nanometer. So that's good. You get it? So what is used is X-rays. So you shine X-rays through a crystal, what will happen is you get a crystal diffraction taking place. And you can take a picture of that, and looking at the crystal diffraction, you can find out some important information about what angles it's getting diffracted through. And so looking at those angles on the screen, you can actually figure out the lattice spacing. So to learn more about a crystal, you go to that branch of learning. What is that called? X-ray crystallography. It's called X-ray crystallography. So if you want to study crystals, you put crystals, shine X-rays into it, do the same kind of spectral studies, and look at the angles of diffraction. So you know the angle of diffraction, and you know the order you're talking about, and you know the wavelength of the X-rays that you have used. Therefore, you can figure out n, and the n is 1 over d, and the d is the spacing. You get it? So more information about crystals. more information about crystals are obtained by spectral studies. And what is spectral study? X-ray spectrograph. Gamma rays can be used if it is still finer. If the spacing is still finer, then use gamma rays. So that will be, it will produce an image. So you can actually study the pattern that is produced and then learn more about it. Now, coming back to interference. Have you seen interference with your naked eye?
Up there, isn't it?
Where?
Whenever you shine the light.
Yeah, but anywhere else, have you seen interference? Interference is what? Constructive and destructive?
Waves.
Mhm.
In the ocean.
Waves in the ocean.
Yeah, two waves come together.
What is the condition required for interference to be visible? Conditions, I wrote down the conditions last class. 1, the sources must be coherent, which means they must be of the same amplitude, they must be of the same wavelength, frequency, and phase. The second condition required is the wavelength should be in the visible region. And it should be, if it is red, it's better. Okay? And the other condition I told you is there should be approximately same amplitudes. So, if you want interference to be visible by your naked eye, you need all these conditions to be satisfied. And definitely you have seen interference with your naked eye. And where have you seen interference? Yes?
On the back of CDs and DVDs.
Yeah.
Oh.
Have you seen colors coming from a CD? That is interference straight away.
It's like gas.
Yeah, the CD is actually colorless. A CD is actually colorless. Oil leaks on the road. When the oil leaks on the road, it leaves patches. And when you look on a sunny day, when you look at the oil patches, you can see beautiful colored rings, right? Where? And soap bubble, exactly. As soap bubble, soap solution is colorless. Then how do you get all those beautiful colors on the soap bubble? That is interference. Yeah, that is all interference. Let me explain a little bit about interference. So, so what happens? Interference was observed again by Newton, and it's called Newton's rings. Now, what is a Newton's ring? This is what it is. So, this is a block of glass, and what Newton did was he put a lens on top of this. He put a lens on top. And then he kept some light source here, and the light went from here like that, and he put a piece of glass at 45-degree angle and let this shine down. So the light was coming down. So what happens to that light when it comes down? It comes to the lens, and a little bit will be reflected, but majority will be refracted. So it goes down. And when it comes here, from the bottom of the lens, some light will get bounced off. And then some part will come through, and then there will be bouncing like that. So can you see there are two stages of reflections taking place. One from the bottom of the convex lens, and the other from the top of the plate. And they're so close that these two will suffer a path difference. They're suffering a path difference now. So these two suffer a path difference. How much is the path difference by looks of this? No, path difference. How much is the distance difference? It's like this. The two rays are going like this. One bounces off here, but the other one goes till here and bounces off. What's the path difference after they bounce off? Okay, imagine there are two students. Who are walking up together. The intention is to go and touch the board and go back. But they both walk together. One comes till here and returns. But the other one goes on till here, and then starts returning. What is the path difference between the two after they move?
One is behind the other.
Yeah, one is behind. So, okay, listen up. Listen up. This is one point. The two people are together. The two are walking together. Watch. The two are going together. And one starts returning and the other one is still going through. And then the other one also starts returning. What is the path difference between both of them after they bounce off? No.
2 times the distance.
Say that again?
2 times the distance between them.
Exactly. 2 times this distance. 2 times that distance. And the same thing applies here. You get it? Yeah. Just see this. Imagine this is 1 meter. Okay, this is 1 meter. One guy bounces off from here and starts moving. And the other one goes till here and then starts moving. Now, after they start moving, they are separated. They were together before, now they are separated. By how much are they separated? By 2 meters.
Okay.
Make sense now? Because one gets bounced, one is bouncing off here and then going back. And the other one is traveling this distance and then doing the same action. So therefore the total path difference is going to be twice this gap. Do you see it? Now, if that path difference is equal to a condition that satisfies the condition for destructive interference, what will happen to those 2 rays? They will interfere destructively. What if those 2 rays are matching up the condition for constructive interference? What will happen? Then it will be constructive interference, more brighter. Do you get it? So therefore, different rays are coming and hitting here and different rays are coming and hitting in different spots. They are going to suffer what is known as interference. Each ray is going to suffer interference. Some constructive, some destructive. Now, there is another concept here that you need to be aware of. One is, it's something that we did in waves last year. But let me explain it to you in terms of light. In terms of light, suppose it is a dense medium. So if the ray of light is coming from a rare medium, and then if it bounces off, it suffers a path difference of lambda over 2 straight away. I'll show you this. So if a wave is going like this and hits like that, the one which is bouncing back is going to be see this. It came and hit here like that. The bouncing back is that way. How much is the phase shift? Pi. Pi is the phase shift. Or in terms of wavelength, half a wavelength. Do you get it? Now this is what happens on a dense medium. But on a rare medium, means like you're coming from the dense medium and then reflecting at a rare medium, this is what happens. The light goes and hits like that, and then the reflected part will be exactly the same thing. It just comes back the same way. No phase change, no path change.
Only when
It doesn't move. I know you just drawn it like this to demonstrate the difference. It doesn't move like a physical distance.
No. This is just way I'm just showing you. So when light bounces off on a dense medium, it suffers a path difference of lambda over 2. When a ray of light hits at a rare medium, it does not suffer any phase change. Yeah.
So if a ray of light is hitting a dense medium, then it bounces off and hits the rare medium, will it change?
Wherever you're looking at one reflection at a time. At a dense medium, it's going to suffer a path difference. At a rare medium, no changes. At rare medium, no changes. At a dense medium, changes are taking place. Okay. Now in waves, when we did waves, we were talking about fixed boundary and free boundary. Remember, fixed boundary. At a fixed boundary, there will be inversion. But at a free boundary, there won't be any inversion. It just comes back same way. Yeah.
So does that mean that if you're just shining a ray of light into a dense medium, that you shouldn't see any reflection because they should destructively interfere? They're just like flips, pretty much like.
I mean, when you are observing the reflected one, you're not seeing the ongoing one. You're only seeing the reflected one. Okay, we have to talk about this here. What's this? Where is the first one getting reflected?
Off the lens.
At a rare medium or at a dense medium? That's my question.
Rare.
At a rare medium. You see it? Okay, look, I'm magnifying that part. I'm magnifying this section. The first one is bouncing here, which is a rare medium. Shh. The first one is bouncing here, which is a rare medium. You see it? This is a rare medium. So it's bouncing at a rare medium. So this one suffers no changes. But the next one is bouncing at a dense medium. So that suffers a phase change of pi, which is equal to a path change of lambda over 2. So there is a phase change automatically. Now, what is the path difference for two rays bouncing right at the center? One is bouncing from the bottom of the lens, the other one is bouncing from the top of the glass, but there's no path difference. So the two rays that are bouncing off from the center, there is no path difference as it is, but because of this concept, there is a path difference of lambda over 2. So what kind of interference will these two undergo right in the middle of the lens? Constructive or destructive? Destructive because of this condition. So what kind of interference you'll see is destructive, that means it'll be dark. So if you're going to use a monochromatic, now where are you going to observe? You're going to observe from the top here. That's why you use a transparent sheet of glass. The transparent sheet of glass will actually bounce the light in, and then this part is going through into your microscope, and you can see it through the microscope. Now, what will be seen as a consequence on the microscope screen? What you'll see on the screen, at the center, you'll see a dark patch. If you're using monochromatic source, one wavelength. And then, from these points corresponds to a certain gap, and with that gap, the total path difference created from here to here, if it is exactly another lambda, you will see a ring. Why ring? Because it's symmetric on all sides. If you're talking about a lens, right? The same thickness you can get all around. So you'll see a ring. What about from here to here? You'll see another ring. And then you'll see another ring. And you'll see another ring. So you'll see a bunch of rings like this. And these are called Newton's rings. You cannot see with your naked eye. So if I take a glass block and put it there, and put a lens on top, and I ask you to look from above, you won't see Newton's rings. But are they there? They are. To see them, you need a microscope. If you kind of use a microscope and see right in the center, you will be able to see Newton's rings. Those are called Newton's rings and produced by interference. Now, if you look up Newton's rings online, you'll see that pattern. You can look it up. Look up Newton's rings online, and you'll see the pictures of Newton's rings.